All right, we're going to look at some questions that have to do with two types of measurements, either vectors or scalars. We're going to talk about how you can tell the difference between them, what they mean, what their purpose is, and how we're going to kind of use them in physics. So let's start up an attempt on here. Okay, and some of the order of the questions on here might be a little bit different based on how early or late you're looking at the assignment. I sometimes switch around the question order, so I just have to the question should basically be the same, but you might just have to do them in a different order than what's in the video here. Okay, so I've got a beaker of water in my classroom that I'm going to end up heating up, and you won't see that in this video, but it raises temperature from 20 to 80 degrees Celsius. Okay. From that temperature change, I can calculate a change in temperature based on the final minus the initial temperature that the water had. So this is something we've seen in a past assignment, hopefully. So all I have to do is take the final temperature minus the initial temperature to figure out the temperature change. If it's positive, that means the temperature is increased. If it comes out negative, that means the temperature is decreased. It all kind of depends on whether this is subtracted here, if the initial measurement was bigger or smaller than the final measurement. So in this case, our final measurement is the 80 degrees Celsius. Okay, let's highlight this. That's the, oops, what's the final? Okay, and this, let's do a different color, let's do blue, is our initial measurement. Come on. I guess I'll just do it in pieces. Okay. So if I take 80 degrees Celsius minus 20 degrees Celsius, either on a calculator with some good mental math, should come out to be positive 60 degrees Celsius. What that means is the temperature has risen, it's gone up, it's gotten hotter by 60 degrees Celsius. Okay, so that's nothing really new. It's just a way of showing that the measurement has changed, and whether it's positive or negative kind of gives us an extra bit of information about that. Okay. Now, I can also do a demonstration with this hot water where you put the water into a syringe, you plug the end of the syringe, and then you pull up on the plunger to decrease the pressure on the inside. Okay. Now, the trick to this, the interesting thing, if you were to see this demonstrated, is that the water inside can start to boil at a temperature below its usual boiling point. Okay. Usually, water boils at 100 degrees Celsius. But even just at 80 degrees Celsius, we can get it to boil if we decrease the pressure. In other words, if I pull up on the plunger of the syringe and give the water more room, then I won't be pressing down on it as much, which means the water can escape from itself a little bit easier. If you think of the water being made as a bunch of little particles, wiggling around, their temperature is basically their way of measuring how fast those particles are moving. So a higher temperature means the particles are moving faster. So the boiling point is basically when those particles are moving fast enough to fight the attractions between each other and escape each other. Now, I can get a liquid to boil by either making the particles jiggle around and move fast enough to get away from each other and have enough energy to escape each other, or I can lessen up on the pressure pushing them together so it's easier for them to float away from each other. They don't have to be moving as fast or have as much energy. Okay, so by decreasing the pressure on the water, I can make it boil at a lower temperature by lowering the pressure. Okay, so that's just kind of the demonstration that goes along with this that you're kind of missing out on. But you could probably find a demonstration like on YouTube or something of this being done. Okay, so the change in pressure that happens in the syringe is going to go from 101 kilopascals to 30 kilopascals. So kilopascals is just a unit of pressure that we use commonly in physics. You'll recognize the kilo prefix from like kilograms, kilometers. So pascals is just a pressure unit that we can tag on this kilo prefix onto. Its abbreviation is kPa, so that's just a unit of pressure. Okay, so if we wanted to calculate the change in pressure, just like with the change in temperature, we take the final pressure minus the initial pressure, where this capital P is representing pressure. So our final pressure in this case was 30 kilopascals, and our initial pressure was this 101 kilopascals. So if I take 30 kilopascals as my final pressure. Oops, missed the L there. There we go. Minus our initial pressure, which was this 101 kilopascals. Okay, so minus that. Okay, I should get a negative number this time because I'm going to be subtracting by a larger number. So 30 minus 101 should give me negative 71. Okay, now just like with the change in temperature, whether it's positive or negative gives me a little bit of information. Since this change is negative, that means the pressure is decreasing. I'm kind of loosening up the pressure that's pushing down on this. Okay, now there are other ways that we can have a measurement bring extra information with it. So say the force I'm pulling up on the plunger with. Force is usually measured in newtons, but force kind of has to go in a specific direction. Like I can't just say, I'm doing 10 newtons of force and have that mean something. Is that me pushing something with a force of 10 newtons, or is it something getting pulled with a force of 10 newtons? Is my weight, on the ground exerting a force of 10 newtons, or am I pushing up by 10 newtons? Where's that force going? A force doesn't really make sense without a direction. Okay? When a measurement comes with a direction as a part of it, we have a special name for that. We call it a vector quantity. Okay? Where quantity is just a number. Okay, and the vector just describes that it's got a direction to go along with it. It's kind of carrying a direction along with that measurement. Okay, so the force upwards on the plunger not only implies that there's some measurement, some amount of force, but also that it's going upwards. It's going in a specific direction. Okay, so force is a vector. Now, one of the ways I try and remember this is the V in vector always looks like kind of the arrow point to me, like if you're pointing in a certain direction. So to remember that vectors have directions, I think of that V as being the arrow point. And so it's pointing in some direction. The vector has that point that's pointing in a direction of that measurement. Now, if you're dealing with something that doesn't come with a direction, like temperature or pressure on their own, then that's what we call a scalar quantity. Okay, scalar just means that we only measure it based on the scale of it, the size of it. So how high or low that measurement is all that matters. It doesn't have a direction that goes with it. You don't really have, a cup of water sitting out at 25 degrees Celsius left. That doesn't make any sense. It's just 25 degrees Celsius. Pressure sometimes is sort of explained as like, I'm pushing on something, but when it comes down to it, pressure is really about force on a specific area. And in the end, we don't really measure the pressure as, it's being pushed in this direction. That's the force we're talking about. The pressure itself is just an amount of that force on a specific area. So pressure is actually a scalar also. Okay, and the way that I like to think about this to myself to kind of get myself out of the direction mindset for pressure is like with a balloon. If you inflate a balloon, you blow air into it, it stays filled up when you tie it. And that pressure is not just going up, and it's not just going down or left or right or back or forth. It's kind of pressing in all directions. So that pressure is something that's on the inside of the balloon. It has pressure. It has a specific amount of pressure, but we don't really bother saying exactly where that pressure is pushing because it's probably in a lot of different directions, or it's going across a wide area. It's not just one single direction. Okay, we can't just put an arrow to show exactly where the pressure is pointing. Okay, so temperature and pressure are scalar quantities. Okay, they just depend on scale. Force is an example of a vector, okay, that has to depend on direction also. So it carries with it a little bit of extra information, not only how much force there is, but also what direction that force is going in. Okay, now these are not the only scalars and vectors that we run into in physics. Let's look at some other examples. Okay, so just kind of as a review, vectors are numbers that have not just a value, but also have a direction. They have value and direction. Scalars are just numbers. They're just numbers that have value. No direction attached to it. It's just a number. It just depends on the scale of it. Okay, so we have these two balls falling here. One of them's kind of going off to the left and also down, and one of them's just going straight down. Okay. Now, there are a couple of things we can measure about this ball, like how far down it falls to the ground. So I could kind of say that in two ways. So if I say that the ball has moved 5 meters, that tells me kind of the distance that the ball has traveled, but not much else. Like if I didn't show you this picture, I blindfolded you and I said, the ball moved 5 meters. Okay, well, I mean, did it get 5 meters, to the left, or did it go down like in the picture? Did someone throw it 5 meters up into the air or roll it up a hill? Who knows? It doesn't say. There's no direction attached to this measurement. So this is going to be a scalar quantity. Okay. Just because the ball moved and it had to have changed locations doesn't mean that the measurement is going to tell us that. Okay, so if the measurement is just the number alone, that is going to be a scalar quantity. Okay, specifically, we do call this distance when we measure out how far something moves and changes its position without telling what direction it goes in. Okay, now if we do include the direction, like I say specifically, the ball moves 5 meters downwards. That is a vector quantity. Okay, because I'm including that direction where that kind of movement is pointing in, where it's going. Okay, now if we just call this distance all the same, then it could get a little confusing because I could say, the ball has gone a distance of 5 meters downwards, but it's like, okay, well, I thought distance was a scalar, not a vector, but you said downwards. So there's technically a different term for when something moves from place to place in a specific direction. We don't call it distance in physics, we call it displacement. Okay, so you can think of displacement kind of as the vector version of distance. Now, sometimes I will still, go back and forth between these terms like they're interchangeable. And so I'll say, something goes a distance of, 3 meters to the left or something. And that happens. So it's not something I'm a huge stickler on or anything. And I don't think you should be either. I won't quiz you and be like, which one's distance and which one's displacement, which one's the vector and which one's the scalar. But it does help to recognize that these are two different terms that have different meanings. So that way, if you see the word displacement, you can say, that has direction attached to it, okay? It's not just something going from one place to another. It's specifically going in one place to another in this direction, okay? It's a vector. Whereas distance does not include anything about the direction. It's just moving that far. Okay, now we can do other kinds of vectors and scalars. So let's look at another example here. Okay, so let's say we're not just looking at how far the ball moved, but also how long it takes to get that far. Okay, so we can talk about the rate of the ball's motion in terms of, say, meters per second, kind of like miles per hour. In this case, again, we're just saying that it's moving at 5 meters per second. We're not saying that it's moving 5 meters per second as it falls downwards, or we're rolling it 5 meters per second, or throwing it upwards at 5 meters per second. We're just saying that it's moving at 5 meters per second. We're not really specific about the direction. So this would be an example of a scalar quantity. Okay, and typically when we talk about how fast something's going, we use the word speed. Speed is another way of saying the rate of something's motion. But we can also be more specific about speed being in a specific direction. It's like if I say the ball is moving 5 meters per second downwards, okay, that adds a little bit of extra information to this measurement. It's not just the number anymore. It's also the direction. That would be a vector. Okay? And if we are talking about speed as a vector, we don't really call it speed, so it doesn't get confused as being a scalar. It is a vector. It does have a direction. So when we talk about the rate of something's motion as a vector, we call it velocity. Velocity is the vector version of speed, how fast something moves. Okay, so you've probably heard of velocity, and kind of like distance and displacement, you've probably heard these pretty interchangeably. Now, you probably don't hear the word displacement in day-to-day speech as much, but you've probably heard the word velocity here and there. So specifically, velocity has to do with how fast something's moving in a direction. It's a vector. Okay, it has that direction associated with it, and that information is included in the measurement. All right, so let's look at a couple more examples on this last page here. All right. So the last couple of days, I've been watching my cat as it moves around the living room. So my cat Marcy loves to jump around on things. She likes to figure out how high she can climb on stuff, on boxes, on the couch, on her cat tower, just about anything she can, leap up to as fair game for her. So what I did was I graphed out my cat's motion as she moved around the living room. So on this graph here, we have an x-axis, which is kind of showing her left to right position in the living room. We also have a y-axis, which is showing her position up or down. So basically how far off the ground she was. So the middle of the living room here is at 0, okay? And the floor is at 0. So if she's moving off to the right, that means she's going to the right side of the living room. If she goes into the negative side, she's going off to the left. And if she is going upwards, it's going into the positive. And thankfully, she's not able to phase through the floor, so she can't go below this kind of 0 point on the y-axis. Okay. Otherwise, that would be a little bit hard to handle her if she can just move through walls and floors and things. So as my cat Marcy is moving around, I graphed out this motion. Okay, where all these D's represent distances. Okay, so D1 is the distance that Marcy moved as she went from kind of the middle of the living room over to the right a little bit. This is going to be measured in meters. So going from here to here would be 0 to 4 meters. So she's moving 4 meters to the right in this case. Okay, from there she moved, let's see, from the floor up to 6 meters here. So from 0 meters to 6 meters is 6 meters. From there, she moved from 4 meters to 8 meters, which is another 4 meters. And then she moved from 6 meters to 8 meters up, so that's another 2 meters. And so as we're going through this, we're going to be adding all these distances together to figure out the total distance that she moved. Okay, so whether she's going left or right or up or down, it's all distance. She's moving. Okay, so she's going to go right by 4 meters. She goes up by 6 meters. Well, that's still distance. She's still covering ground. She's still changing her position. So even though these are going in two different directions, right and up, distance is not dependent on direction. We're just adding up these scalar quantities, just these numbers. So I'm going to be adding 4 meters and 6 meters here to say that she's covered an added distance of 10 meters from here to here. Okay. As she goes on to go through this little D3 segment here, that's another 4 meters. So that takes us to 14 meters. She goes up by 2 meters from 6 to 8. So that adds another 2 meters on. She goes to the left a whole bunch. Something to be careful about with this. When you cross an axis like this, it can be kind of hard to keep track of how many meters she's actually moving. So like if I were like just looking at this at a glance and I said, okay, well, I'm starting at this x equals 8 meters here, and I'm ending over here at x equals -4. 8 and -4 makes +4. Except we're not really subtracting. We're kind of going from here to here. You can kind of think of it like 8 minus -4. Okay? So the other way that I like to think of it is from here to here is 8. From this point here to this point here is 8. And from this point here to this point here, from 0 to -4, is another 4 meters. Again, the distance just depends on how far she's moving, whether it's left or right. So in total, she's moving 12 meters from here to here. So if you add up the 4 meters here, the 6 meters here, another 4 meters here, 2 meters here, 12 meters here, another 4 meters here, and 2 meters here, this should come out to be about a total of 34 meters, okay? And again, that can be some good mental math work, or it could be using your calculator, okay? So in total, Marcy is traveling 34 meters as she's going right and up and right and up and left and down and right, okay? So this total distance does not tell us anything about which direction she moved. It's not like she's going 34 meters just upwards. That would be really, high up in the air. But it's not that she's going 34 meters just to the left. She's going a number of different directions here. And we don't really care about which direction she's going, and we don't include that in the measurement. So this is a scalar quantity. Distance is scalar. Okay. Now we can also describe her directions as vectors. So to do that a little bit more easily, since we're going in multiple directions here, since Marcy is moving not just left or right or up and down, but both, we're going to split those up into what we call components. Okay, so we're going to have just the x components, just going left to right first, and then we're going to look at just the y components, where we'd just be going up and down. So let's look at the x components first. So this is Marcy's horizontal movement, shown in red, and everything else is kind of in grayed out. So Marcy moved right, and then went right, and then went left, and then went down, and then went right. Okay? So we're just going to be focusing on how much right and left she went. Okay? So we're going to calculate the horizontal displacement, okay, which is going to be basically the change in x, okay, which is going to be the final x value minus the initial x value. So her final position, after all this, was x equals -2. That's where she wound up, okay? -2 meters from her starting place at the center of the living room. Okay? In other words, 2 meters to the left, okay? So to go from the start to the end, if I just care about the difference in where she started and where she ended, I kind of ignore all this huge path that she took to get there. The only thing I care about is where she started and where she ended. Okay, so if I take her ending, her final position, minus her original initial position, -2 minus 0 is going to be -2. Okay, so Marcy's horizontal displacement is -2 meters. Okay, in other words, to the left. Okay, so this comes with a direction. It's not just that she moved, 2 meters or -2 meters. It's specifically 2 meters to the left. So this is a vector quantity. Okay, and we use that negative to imply that she is moving to the left. Okay, her change is going from some place to another, and that direction that she's moving in is leftwards. Okay, now kind of like what I mentioned before with changes, when we do like a change in temperature, a change in pressure, a change in time, it kind of comes with some extra information, and that's what's going on here too. Okay, and it doesn't really matter where exactly in the living room she started and where she ended. Okay, what matters is how far she moved from beginning to end. If we just compare the very beginning measurement and the very end measurement, and that's how we get this -2 here. Okay, now let's look at the vertical movement. Okay, so here we've got that she went up and then over, and then up and then left and then down and then right. Okay, so we're just looking at these blue arrows here. So her vertical displacement is just going to be the difference between where she started and where she ended, going up and down on the y-axis. So she started on the floor at 0 meters, and she ended up about 4 meters off the ground here at the end. So the difference between this final measurement of 4 meters and the initial measurement of 0 meters is going to be our change in y. It's our delta y, our change in vertical displacement. Okay, and that is going to be 4 minus 0. So 4 meters. And that carries with it a direction. From start to finish, she moved 4 meters upwards. Sure, she didn't take just that path. She went kind of the long way around, but she did end up going 4 meters up. Okay, that's what displacement is. It's just a difference between a starting and an ending position, and it kind of ignores the path that you had to take to get there. So she moved 4 meters, and the fact that it's positive means that she's gone upwards from her starting point. Okay, since it's carrying a direction with this measurement, that is a vector quantity. Okay, so both horizontal displacement and vertical displacement are both vectors. Okay, distance is a scalar quantity. It does not come with a direction. We're only talking about how far something went, period. That's it. Okay, so we'll be using more stuff like this with vectors and scalars as we go through physics, and we'll look at how sometimes vectors are really important with that extra information. Sometimes scalars are just as important because we don't need that extra information sometimes. Sometimes we bring them together into the same equation. It just depends on the situation that you're trying to describe with your measurements.